Excellent. All right, let's make a start. So thanks everyone for coming. Welcome to GPT on a TPU VM with PyTorch XLA. I guess I should say PyTorch / XLA. So I am going to present a workshop today. Hopefully you guys can follow along, and the intended learning outcomes are to learn a little bit about TPUs, tensor processing units, the VMs or virtual machines they run on, accelerated linear algebra, which is the compiler that translates our code to run on the TPUs. And that the motivation for this is that we're doing a lot of experiments in this group, mainly to scope out developmental interpretability as a technical AI safety sort of research direction. And those experiments use a lot of compute, and TPUs can potentially help us make that process go faster. So we're also going to have a practical element of today's workshop, which is that we want to access and run code on TPU VM. And so there's a couple of stages that'll involve. So we have to get the code onto the TPM, and we're going to use GitHub for that. We have to train the code is pre-prepared with a GPT-style transformer training loop using PyTorch. So we'll first run that on the CPU, and then we'll make some modifications to that and run it on the TPU using PyTorch / XLA. And if we have time at the end, I'm going to point you in the direction of applying for your own 30-day allocation of free TPU VMs on Google Cloud Platform. So I've already discussed with you guys the prerequisites, but if any issues come up, you can ask questions while we go through. Yeah, so we're going to break this down into a few steps. So the first step is to secure SSH access to the TPU VMs. So this is going to involve you guys generating a key and then sending it to me, and then I'll add it to my list of approved keys on my Google Cloud Platform account, and then send you an IP address, and you should be able to get in with SSH. We'll do that in a moment. Then we'll try and get the code onto the VMs. We'll train the transformer on the CPU, like I said. We'll make some modifications to make it train on the TPU. And then at the end, like I said, if we have time, you can do. I'll point you to the application for your own TPU VMs for your research. And yeah, we're also going to sort of punctuate each of these steps with a little bit of background information on TPU VMs, SSH, GPT, XLA, GCP, and the TRC. And you might be thinking, WTF? There's a lot of acronyms. And so I just want to start by breaking those down in case anyone's not aware of some of these, because we want you to understand what I'm talking about. So a TPU is a specialized processor like a CPU or a GPU, but it's designed by Google to execute large batches of neural network operations like matrix multiplications more efficiently than on these more general purpose processors. And I would recommend pointing you to the Wikipedia article for the history of TPU development, and Google Cloud has a blog post on sort of a conceptual understanding of how TPUs work, and also a discussion of sort of the kind of code workflows that they are and aren't useful for. So we access these TPUs via virtual machines or VMs, and a VM is just you can imagine it basically just like a server out there that's sitting and plugged into the wall and connected to the internet. It offers the same functionality as a full operating system, but it's just a little bit more efficient for the providers because it's running on shared hardware. So when you're not using it, they can be using that hardware for someone else. And in our case, the main hardware we're interested in accessing is a TPU. And so a TPU VM specifically is a VM that has access to such a TPU. A third one that may be new to some of you is XLA, for accelerated linear algebra. This is a compiler that takes computational graphs. So like when you write a Python program that says a bunch of matrix multiplications in a certain order, that generates you can think of that as a computational graph. And so XLA takes such a graph and transforms it into an efficient instruction sequence for specific hardware, including CPUs, GPUs, TPUs, and other machine learning hardware. So XLA is not specific to TPUs is a consequence of this. But at the moment, as far as I understand, running code on a TPU requires XLA because the TPUs don't run uncompiled computational graphs. They kind of require a compilation step, whereas CPUs, you don't need this sort of optimizing compiler step, or it's a little bit more straightforward, or I don't know what PyTorch is doing under the hood to get your operations. I guess it's just using like BLAS and LAPACK and stuff like that. But anyway, which are compiled programs that it's like calling into. For a TPU, we need to kind of compile it every time. That's my understanding. So that's why we'll be using XLA today, and it's sort of an extra step on the way. Oh, and also PyTorch / XLA is different from XLA. It's the library that bridges XLA and PyTorch. So I'll be referring to that as well. Okay, so SSH. SSH, or the Secure Shell Protocol, is a long-standing Linux or Unix tool that allows you to, well, actually the protocol, I guess, is more general than that, but mostly it's used by people accessing like Linux servers and stuff. And so for us, it's basically lets us open a terminal on the TPU VM without being there in person, like with a keyboard and a monitor physically plugged into the hardware. And to make this connection, you need an SSH client on your machine, and we're going to be using the sort of standard terminal client SSH, although there are many other clients. Hopefully you will have access to this one. It's the sort of simplest and just does it straight in the terminal. There were a couple of other acronyms that I mentioned just quickly. GPT, Generative Pre-trained Transformer, hopefully you're mostly familiar with this. GCP, Google Cloud Platform. So I was somehow more familiar with Azure and AWS than GCP, but yeah, it's just another big data center out there with a lot of hardware, and they rent it out to people. And this is where my TPU VMs live. And the TRC, the TPU Research Cloud, is a program run by Google Research, which aims at supporting machine learning research by offering researchers free Google Cloud Platform compute resources, and including the TPU VMs that I'm using and that we'll be using today. And we'll talk about more about how you could apply for such support later. So we'll quickly go through some steps to get you guys access to the TPUs, but are there any questions so far?
From me.
If not, let's get started. So the goal of this first part is to get you guys shell access on a TPU VM. If you want shell access on a TPU VM, you first have to get a TPU VM, which you could pay for, or you could apply for a free one. You can do that later. Today, I'm just going to configure you guys shell access an account on one of my TPU VMs. So there's a couple of ways that you can actually do it. Like I mentioned, as a joke, you can go and visit Google's data center with a monitor and a keyboard. That'll take too long. You can use the Google Cloud Web Apps built-in shell. That will also take too long because it's really laggy and browsers are really slow. You could use a graphical SSH client, but we're just going to use SSH. Hopefully everyone has that. So there's, let me see, 3 steps to do this. First, you have to generate a key pair on your device. So this is like something, you're going to generate a private and a public key. I'm going to add the public key to a list of approved public keys, and then you're going to be able to log in with your private key, and Google is going to be able to verify you by checking it against your public key. So to do this, everyone should open their shell, run the following command, and I'm going to demonstrate this now. Let me see. I wish there was a way to share just like 2 different windows at once. I think I might end up sharing my whole screen. I'm just going to need a moment to refactor my window. Share entire screen. Hopefully this is still fairly clear. So we're going to run a command ssh keygen. We're using the key type ed25519 because that's what GitHub does. I think for most of you, it should be fine to put it in a location like home directory, which might be different on Windows, .ssh/ and then I'm suggesting that the title of the key is Matt's TPU VMs, because then it will get you into all of the VMs, not just one. And if you know the IP addresses, and this will help you remember what this key is for later. And we also need to add a username. So just pick a short lowercase name. So it will ask for a passphrase. You don't need a passphrase. Generate a random art image. I never checked that. And now, if we go to the folder .ssh, there will be in here 2 files created, one called Matt's TPU VMs and one called Matt's TPU VMs.pub. What I need you to do is step 1.2 now. We're going to add the contents of this public key file to my GCP thing. So we need to open that file and copy the contents and send me those via Discord, and I'll add them to the TPU VM. So this will take a few minutes, but if everyone could please go through these steps if you want to use TPU VMs, and you can just paste it in either a DM to me or the meeting chat. It is secure to send me your public key, but you shouldn't send me the private key. So make sure you, oh yeah, but by the way, this is what it looks like. Make sure you do the .pub one. It's just a string like this. It's secure to show this off even on a recording. No one can do anything by just knowing your public key. You just want to keep the private key secure. But while we're talking about security, I want to note that giving you guys access to my TPU VMs, you'll have root access, and anyone with root access on a Linux machine can see everything on everyone else's account, which this will automatically create accounts for all of you. So I'm going to see if I can strategically like hide the IP addresses rather than just dumping them all together in the chat or in the recording. But if you're worried about people, for example, getting into your machine, or me getting into your machine and like getting your GitHub key and doing something with your GitHub account, then we're going to want to find a workaround for that. So the keys themselves are secure, but then the machine will sort of allow us to use those keys to kind of see each other's GitHub keys and stuff. So
the point being,
hopefully it's fine for today.
The point being, in a later step, we're going to create a private key on the TPU VM to
that's right,
clone
exactly.
the GitHub repository. Yeah.
Yeah, thank you. So by having root access, you'll be sort of sharing that private key with me at least, and potentially everyone else in the workshop. But I think that you guys are outside of my threat model, so I'm happy to do this with you, and hopefully that's okay for today. And I'm looking for a better way to kind of arrange this part of the workshop in case I want to run it again, also with people that I'm less close with. Okay, anyway, without further ado, let me start doing some of the steps. So hopefully you guys are sending me these on Discord. I can hear that popping off in the background. So I'm going to pause the stream and start copying these across to GCP. Billy, there's one spare TPU, so you can also join in. Okay.
Are these instances not ephemeral?
No. I mean,
okay, so they are.
Yeah, I might eventually shut them down. But is that your question?
Yeah. So I just thought like if these security issues should just go away if the machine changes and got shut down.
Sorry, who are you asking?
Yeah. So oh, sorry. Can you hear Edmund, Billy?
No, I can't.
Oh, maybe that's the problem.
Oh, somehow I have. Sorry, I have them muted. Never mind. I don't know.
Yeah, I was just answering a question from Edmund, which is, are the TPUs ephemeral? And then the security issue would just automatically go away. But that's not the case. These are my sort of like permanent allocation, and I'm sort of keeping them online for like the next couple of months. But you can just revoke the GitHub key after the workshop if you want. Okay, let me see. Who haven't I got a key from? I think, have I got a key from Justin? Okay, I'm waiting for a key. Oh no, I lost my, where's the voice channel? Okay, I'll add these keys and then I'll just check if anyone else. So saving these keys to my profile, that'll create some accounts. What I'm going to do now is send you guys an IP address that you can use in the next step. So I'll send that to you guys via DM. It's just going to take me a moment. I have to click back into the voice call every time. Oh, I haven't got a key from Justin because I forgot that he hasn't joined us yet. Zach, here's your IP address. Billy. There aren't that many steps like this where I have to do something for everyone. There's a bottleneck. Okay, I believe I've sent everyone a IP address. If anyone is missing that, oh yeah, like Liam said, except for Liam and Jesse, who have already gone through the steps of setting up their own TPU VMs and will be following along there, if I'm not mistaken. So I'm ready to share my screen again. And we will resume these steps. Thank you, everyone. Here we are. We've just finished step 1.2. I've added the public keys to my TPU VMs. And in step 1.3, one of those steps is that I send you an IP address, and I've done that. So now what you need to do is open your shell and run the following command. So we're going to SSH with the identity file from the key path. So in my case, that's home directory /.ssh/mats TPU VMs. Actually, I think for me, I didn't add my own key to the thing, so I'm going to use the old key that I've been using. You have to do the private key, so like not .pub. Actually, I guess that's, maybe there's a bug in my instructions. Oh no, that's okay, keypath.pub. Although maybe I could have done that, written that differently. But anyway, and then you want to type your username. So that's Matt at for me, and then the IP address. And let me see, I guess I should just use my IP address. Well, you put the IP address here as I sent it to you. I actually already have these configured in my SSH config. So what I can do is I can just type TPU2A. And that's the one that I allocated for myself to work on. And if you want help setting up this so that you don't have to type out the full command later, then I'm happy to help with that. Just going to check messages. I use the private key to log in. Is that a problem? That's what you have to do. Sorry, I wasn't clear. You have to use the private key to log in. And as long as you didn't send me the private key, we're all good. Okay. So what we've got now is something new. I'm no longer running commands now on my own machine. I'm running commands on the TPU. So what I've done is I've set it up so that it tells me if I'm on my MacBook Air, which is called Atmos, or if I'm on the TPU, which is called TPU 2A in this case. And you guys will have other ones on my TPUs, but you'll probably see a different prompt that has like a weird numbered host name. That's just the default one that comes from Google. You can change that later. For now, what's important is to know that you're now looking at the TPU VM. So let me interlude to tell you a little bit about these VMs. This is a TPU VM. It's running Ubuntu Linux. It has 96 gigabytes of disk space, which you can see somewhere in the startup prompt. And apparently I've used 50% of this one. I don't remember doing that because it starts at about like 20%. Probably yours will be around that. This is a machine that has access to some pretty impressive specs, including a 96 core CPU and 335 gigabyte of main memory. And so I can demonstrate that to you. If I open another shell in here, I can run a command called htop, which will sort of visually show off the CPUs there. They're not doing much at the moment, and there's 96 of them, as you can see. This is showing the utilization for each of the CPUs. I can do something that requires RAM, but I'm running a little bit slower than I thought, so I'm gonna skip this demonstration of like lighting them all up. We can view it later when we do some training. The main event thing that we're here for, though, is the 8-core TPU, and so for most of you this will be a V3, and for some of you a V2. I can figure out which and tell you later, but I haven't really noticed a big performance difference between these when I've been using them, so hopefully that's okay. And the TPUs have some like graphical memory, the equivalent of VRAM on a GPU. They have their own internal memory, and so we'll work now towards getting these, training some models. So the next step is to get some code onto the VMs. But in the meantime, are there any questions? Just gonna be periodically checking the chat. Oops, sorry, I should have IP address.
What does everyone currently have access to when they are logging in here? In other words, are they getting one of your TPUs? Are they accessing the node that has 8 TPUs on it? Like, how exactly does that split kind of work?
Yeah, so I'm adding the public keys to my Google Cloud Platform project that has the TPUs on it. So I think this is gonna mean that any VMs that I create on this Google Cloud project, which is just like a project on Google Cloud Platform, is just like a group of compute rentals. People with the private keys corresponding to these public keys are going to be able to access that compute. But you need the IP address, and so I'm kind of hiding that as best I can, although I think I just flashed the one I gave to Billy a moment ago in the screen share. And so, yeah, you guys have access to all of my TPUs effectively. Does that answer the question?
Nearly. I'll just ask one more thing, which is when Google send us that email that say, you've been given some allocation, and it says 5 on-demand cloud TPU devices, what is the difference between those 5 TPU devices and then the 8 TPUs that you specified this having?
This has... Let me see. So
if you scroll up from here,
8 cores. Oh, that's different. Yeah. Okay. So each of those TPU devices has 8 cores, and there's 10 of them because there's the allocation email says there's 5 V2s and 5 V3s, so 10 total. And I'm using one. One is unreachable, and I'm loaning out the other 8. So we're fully booked today. With one, it's like a full room with one chair sitting over in the corner broken. And each chair is a massive steaming anyway, a virtual massive steaming compute pile. Yeah, any other questions?
So when you're running a suite of 10 experiments, say with different hyperparameters, is that on one TPU or is that across the 10 different TPUs? Like, is it across the cores or the TPUs itself?
I'm doing both when I do a sweep of 40 experiments at once, because you can run 4 experiments at once on one TPU because it has 8 cores, but they're in like groups of 2. So I'm just going to add Billy. I don't know how secure this is. Billy to the repo, and we're ready for the next step.
Just while you're doing that, you mentioned when you showed us HTOP, that was like the 96 CPU core.
That's right.
But where can we see the TPU cores somewhere?
Yeah, no, HTOP doesn't see them. I don't know if there's a tool that can see those.
Okay.
Billy, that'll be you. Zach, just quickly, what's your GitHub username? Maybe.
Yeah, it's right there. Zfurman56.
Cool. Great. Okay, I think everyone is now invited to the GitHub repository, so we can do the next step. So the next step, oh, sorry, that's not the next step. That's a later step, but we're going to need to do that anyway. That's the other thing that I'm going to need to do. So now we can just go through and do some following along with the code. So you guys have to do something to get your GitHub profile able to clone private repositories onto the VM. So I could have made this repository public, and then you wouldn't need to do this step because you wouldn't need a GitHub account to clone the repository. But it's an important step because you need to do it if you want to share your own private code. So this is like a practice run. If you want to get code onto the VM, I think the best way is to use GitHub because GitHub and Git, because it will help you keep the code in sync when you've got multiple versions of it. And other ways of doing it that don't involve GitHub are possible, but a little bit more tedious. So to do this, you're going to have to authenticate to GitHub because, like I said, it's a private repository, and to clone a private repository, you need to use SSH-based authentication with GitHub. And so the steps to do that are to, inside your shell on the TPU VM and not on your local shell, you need to generate another key pair. So we're going to run a similar command again, but this command is going to be creating a key called GitHub. Actually, I'm changing this default name and I don't know if that'll have consequences later, so I might regret it. But you're going to put your GitHub email into the command, and then run SSH keygen again. And I'm once again not going to do a passphrase. And so I think for me, that's going to create in .ssh file called GitHub and GitHub.pub. Last time I did this, I used the default name. So that's the one I generated last time. And then I can look at GitHub.pub. And once again, it's a key of this sort of similar form. So the steps to get this onto GitHub, we'll have to upload it through the website. But before we do that, we're going to have to, I don't actually know what this does, this SSH agent, but this is a step from the GitHub sort of instructions for doing this. I don't know what this does. So we're going to try it. You shouldn't run commands that you don't understand, but nevertheless, we'll do this. Maybe this helps GitHub find it when I'm using maybe this helps Git the command find the key when I'm using it. And so I might as well show you the full steps to go to your GitHub settings, go to your SSH and GPG keys, and add a new SSH key. And this is the TPU demo key. And I need to get the public key And the easiest way to do this is just copy and paste. If you, let me see, so it might not be so straightforward. So to actually see what's inside this, it's on the VM. So it's not as straightforward as opening it in your local text editor unless you specifically configure some kind of sync like with the VS Code or something like that. But what we can do is we can just cat it out, which just appends it to the command line. So I'd recommend running this command, which I should have put in the instructions, because that will just put it on the terminal for you, and then you can just copy it. Make sure you get the whole thing. You can just copy it from your terminal emulator. And so add SSH key. And then that will allow you to clone private repositories on the VM. Just going to check if there are any messages or questions. It looks like we're going all right. We will continue. But yeah, stop me if you have any questions. So I've already added everyone to this private repository, but now we'll be cloning this onto the VM. So everyone needs to run this command, git clone, and then this is the URL of that repository. And I think I haven't done this already on this particular VM, so I'm going to also do that. Should just take a moment to download this rather small repository, and then we can go inside. Oh, wait, that's next step. But yeah, let me tell you a little bit about what this code is. So I've called this repository bite-sized GPT because it's a simplified version of Andrej Karpathy's Nano GPT, based on following also one of his excellent sort of detailed tutorials on how to code up a GPT-style transformer in PyTorch. It's a bit simpler than Nano GPT in ways that we can talk about later. The implementation is also simpler in that instead of like tokenizing or sort of basically just saying that characters are just one of 128 different possibilities that correspond to the ASCII character set. And so we can just directly predict bytes from the model. And the data set we're using is the Sherlock Holmes canon, rather than what Karpathy does in this tutorial is use the complete works of Shakespeare. But, you know, it has some benefits in that the code is a little bit simpler, and I know how to easily modify it to run on the TPU, so we'll do that today. And I highly recommend studying Nano GPT and starting with this tutorial if you're interested in learning how to code up transformers in PyTorch in detail. But for now, let me show you a little bit about what's in this repository. So I think I can go to the actual repository now and show you the main things are this data folder, which contains the data set, the main file that we're interested in being the complete works of, well, sorry, it's not the complete works of Arthur Conan Doyle, but just the complete Sherlock Holmes ones. So we've got a contents page, but then later we've got just, you know, the text of the stories. It has some interesting quirks, like for example, it's always indented by 4 spaces to launch a new paragraph. And one of the things we'll be interested in is whether the transformer can kind of learn to pick up on that. Among also the language, also otherwise the language sort of details and actually spelling words correctly and maybe writing some dialogue or something, but I don't know. I don't know. We'll see if we'll get there. So far, I haven't had that much luck. Okay, so other than the data folder, we've got this script called model, which defines the PyTorch model, and that is just, and a few utilities. That's just a pretty straightforward PyTorch code. We're not going to go through it today. Like I said, if you want details on this, I recommend Karpathy's walkthrough, which will go through all this kind of stuff. But what we will be looking at today in more detail is the train script. So this script, I'll step through now. We have to load the data set. We have to set up an actual transformer model with various parameters. Sorry. For example, embed size, I chose to be 32 in this case, and training a 4-layer transformer with 4 heads per layer. We set up a PyTorch optimizer. We're using Atom. Just doesn't really matter, I guess. And then we're going to go through a bunch of training steps. In this case, 50,000 training steps. In each case, we're going to get a batch, put it through the model, compute the loss and do an optimization step. And then periodically, we're going to do some evaluations. So we're going to record what the training loss was. We're going to get a test batch from an unseen part of the corpus, and we're going to see how the model performs on that and print out that loss. And then we're going to see what the model does to complete a prompt elementary idea and see if the model comes up with something, and then we're going to print that so we can see kind of visually what the model is like thinking that the text, the corpus looks like at each stage of training. And then at the end, we'll run a slightly longer completion and see what it comes up with. That's all. So we can get into the running this.
I'll just flag a couple of things I ran into. So you'll need to pip install TQDM, and I had to do it both as my account and as root because I had to actually do the training step after switching to XLA. I had to use root because I got some permission errors for log files.
That doesn't sound like I was expecting it.
Yeah, I don't. There's probably a smarter solution than switching to root, but that was the...
Yeah, okay. This could be something I wasn't anticipating because we're on like different accounts on the VM or something, and maybe my Python installs that I thought were global actually just to my user or something like that. So sorry about that. I'm now looking in the chat and it looks like there's another problem. Okay, so Liam points out, Billy, if you missed the SSH agent, it shouldn't be necessary to SSH agent every time, was my understanding.
And it's SSH add.ssh, and then like GitHub is the name of the private key I made.
Yeah.
So that's the one I'm adding, right?
Yeah.
I'll see if I can log out and log back into this VM.
Okay.
Try again.
Yeah. Does this need to be SSH? Me.
Worked fine for me, in case that matters, but...
No, it's just meant to be git clone that. Yeah, sorry, I don't immediately know why that would be happening.
What does the eval step do? I did that, but I'm just curious what it does.
I think it spawns the agent so that you can actually like receive this command. So if you
have I failed to like accept an invite or something? Maybe.
Possibly. Oh yeah, that's probably it. So when I added you a moment ago, you would have got an email that you need to accept. Yeah, that'll be it.
Cool. Yeah. I'm all sorted now. Thanks.
Great. Thank you. Okay. Any other issues? Yeah, Liam, I'm not sure why you can't hear Billy. I can hear Billy fine.
If you see like a red slash on anyone's microphone icon in Discord, they are muted by you. So you need to right click them and click unmute. For some reason, I had that on Edmund and Rowan for some reason.
Okay, so anyone who might have manually muted someone, you'll see a red slash on their microphone in case you can't hear Billy because you manually muted him. You'll need to undo that to hear them. Let us press on then. So yeah, we might need to install some things. And so if it was just TQDM, then the command for that is pip install TQDM.
I needed to install Torch.
Also Torch. Okay.
Yeah.
That surprises me because
Torch.
I thought these later Torch what?
Torch XLA.
Okay. Well, I'm sorry about that. I thought these VMs had that because I specifically configured them to have that. So
this is a more more advanced tutorial than it seemed.
Yeah, that's right. But okay, it's just like one command. Torch XLA is a little bit special because it looks like that if you want to install it. It's a little bit special because it basically only runs on these TPU VMs, I think. I don't know if you can get that on your own computer. I haven't really tried, so maybe you can. But it's like tightly integrated into Google Cloud Platform because that's the only place that you can use these TPUs. So yeah, hopefully that doesn't lead to any problems. TQDM is a progress bar library, so we'll see that printing some pretty progress bars in a moment.
Apparently NumPy too. So I think
am I even using NumPy?
Wait, sorry. Okay. Sorry, I'm using my own VM virtual environment. Sorry, I just realized that.
Oh yeah, okay. If you use a VM, then you will have to do this. Yes, that makes sense. Okay, let's.
I've had success after just installing TQDM.
Okay, good. I would recommend people do that if they haven't already, and avoid VMs for today. Let's run the code. So we're in. If you've been following along the commands I've been doing, we're in the home directory, so we need to actually cd into bite-sized GPT folder, and this is where we've got that data and the model and the train script from before. And the command to run this is just python train.py. You know, I mean, it could cause problems. I'm just going to check if the Python version is the one I'm expecting, and it is. I think I installed Python 3 on these VMs, so hopefully for you that's also Python 3.8. So train.py. When you make your own VMs, don't yeah, it's easy to accidentally mix up Python 3 and Python 2, so watch out for that. Why is this not immediately doing something? I was expecting that to immediately do something. Maybe this TPU is a little cold. Not that it's using the TPU, I mean the VM. Okay, it's working. Okay, so this is happening now. Okay, finally. Hopefully yours is also happening. Let me know if there's any problems. You can see the model starting to train. It looks like it's going to take about 20 minutes to do the 50,000 steps. The loss quickly goes down in the first 100 steps by a few points. And you can see it basically learns which characters are realistic rather than printing these weird bytes that never occur in the corpus. It sort of suppresses those in the output, and I don't know if it's getting sort of roughly word-shaped things, but it looks like it a little bit. The loss will continue to slowly drop throughout training in my experience. Just to be clear, what the model is saying, we're giving it quote elementary my dear, and then it decides what comes next. You know, there's an actual word, and that's a word, so it's not so bad. Let us talk about what it's going to take to get this running on the TPU. I'm just going to check if there's anything here. Okay, good. So to get this running on the TPU, we need to use XLA. So that's what I mentioned at the start. And so conceptually, XLA works into the training loop as follows. So as the PyTorch code runs, instead of performing actual matrix operations, the XLA backend is going to construct an abstract computational graph so that then it can wait to see what operations would happen. And then at certain points that we insert in the code, it can say, all right, well, now I'm going to compile and optimize all of those computations into a way that will fit nicely onto the TPU and run efficiently using its specific shapes and characteristics. It will do that compilation, and then it will send the compiled code to the TPU, execute it, and get the result. And then whenever you request a particular value in the code, it's going to do that compilation and then run the code, actually execute it, and then get the value back and give it to you. We can also manually insert points where it's going to do the compilation and the execution. And so PyTorch normally uses this eager execution model, but this is one of the reasons, one of the jobs of PyTorch / XLA is to sort of bring this more lazy TensorFlow and JAX style execution model to PyTorch. That's my understanding. So this compile step that's in the middle there is actually fairly slow. So this only actually makes the code faster if we can use the same code we've compiled repeatedly. So we need to be careful to make sure that our code isn't like our computational graph isn't changing every time we do a loop, because then it would have to be recompiled. So then XLA can, or PyTorch / XLA. Actually, I think this would be XLA can cache the compiled computational graphs.
Can you point out these points in the code?
Yes. Well, there aren't any points yet. We're going to add them. So that's the next step. Unfortunately, it's not as simple as just changing the device to the string XLA. We need to import torch XLA, and we need to actually put these breakpoints into the code ourselves and initialize the device and a couple of other things. So that's the next step. So we're going to do that now. It shouldn't take 10 minutes, but I do think because this is a small training run, if we left this running, it would finish before the XLA version. But I'm going to try. You can quit this if you want. I'm going to try doing it in parallel. See if I can beat it with a TPU. I don't think I'll be able to. It still takes about 15 minutes. So I've got two options for you for how to do this. So if you look around, actually you probably won't have both of the branches, but there's a branch on the GitHub repository called TPU. And if you want, you can just git check out a remote branch origin / TPU. Make that a little larger. And that will, if I get diff from the main branch, that will add a couple of lines of code to the train script, as you can see here. So it's importing this torch XLA, initializing the device. It's only doing this if we're like on the TPU and we've specifically requested the XLA device with a command line argument. And then it's inserting these xm.markStep calls before and after the training step and before and after the evaluation code. And actually, just to note, I think this is probably overkill like afterwards, because immediately after this, we're at the next mark step, or if it's not 100th step, we'll go back to the top and we're at this next mark step. But I like to insert as many as possible because I just want to make sure that they're marked. So that's just a bit of a quirk of my style at the moment. I'm not really sure how to do it in a more principled way than that. But what I'm going to do is I'm going to go to the code. So what you can do is you can check out this branch and then just run Python. I can do this. I'll race them. So Python train XLA will now run this. And then I'll step through the code while it's running, maybe, in case you want to make the changes yourself. So this will now set up the TPU. Takes a few moments. And you're seeing that happening now. It's importing it. This one was slow just to import torch, so this one might take a little bit longer than usual, but now it's done. So now it's initializing the XLA device, which is just like setting up the connections with the TPU or something like that. I don't exactly know what goes on in this step. Just for clarity, this is sort of somewhere here in the code, initializing the device. That takes maybe a few more seconds. Now it's doing the normal things, loading the data, initializing the model, but now any operations are happening on the TPU. So we've done this is before the first step. No, this is after the first step. So you can see it's actually going very slow. This is not what we wanted, but that's because it had to compile the first time. And so now you can see it's going faster, and it's only going to take about 17 minutes for the whole run. On my TPU V3s, it was taking more like 15 minutes. Maybe that's a slight difference because of the architectures. You can see that the iterations per second, which is hovering around 40 here, is gone up to around 50 or up to almost 50. So I'll leave that. Oops. Oh no, I've screwed up my output. That's the problem with binary window partitioning.
Sorry, I forgot how to fetch the remote branch of TPU. I think I'm just
so that one is here. Git check out T origin / TPU.
Right.
We'll do it all in one step. Sorry, yeah, I'm gonna step through the code and talk about where to add those things now while this is running. Question maybe? I haven't seen this issue before. So yeah, that may be the case. So from Edmund, is anyone else getting that permission issue, or is that?
That's the same issue I had.
And you had to run something as root in order to.
Oh, I just ran the whole training run as root, which I'm not recommending. But
okay. I don't know how to get around this. I didn't know that this log was a thing.
Can you turn on that to the most passive thing?
Yeah, just add /temp TPU logs.
So this just needs to be right, I think. So is that 777? So I would recommend running the command
chmod.
Yeah, chmod. I haven't done this in a while. Like that. Yeah, thanks, guys. Great.
Thank you.
So let's talk more about the code. Actually, because we're getting close to the end of time, who wants to see the code, need to step through this in more detail than I already have, versus move on to more info about TRC, Tensor Research Cloud.
What are you going to say about TRC?
Like, okay, the remaining things to say are how to speed things up more than this, and how to apply, and what you actually have to pay for, if anything.
Yeah, I read through all that before. I feel like it would be most interesting for people to see you put in mark step somewhere or something.
Okay, all right, let's do it. So are we in bite-sized GPT? So we want to take the training loop, and we want to make this a little bigger. Okay, I'm going to need to go into the other branch to get this right, because we've already got it here. So now, okay, so what I've got set up here already is that the device comes in as a string, and it's XLA if we want to run on XLA. So what I need to do is have a flag that I'm going to need for all of the mark steps, because we don't want to run the mark steps unless we're using this device. And I could just check device equals XLA later, but this is shorter, as in like if XLA capitals is shorter than if device equals XLA. And also I want to overwrite this device with an actual torch device that comes from the XLA. So now everything I do is going to be prefaced by if XLA. To explain this environment variable thing, I'm actually going to not set it. So I'm going to ignore that and just do this step, import torch XLA core XLA model as XM, and device equals xm.xla device. And so now that device is going to be the one that's passed to the data set. So the data is going to be loaded onto the device, and the transformer is going to be loaded onto the device. Let me see. So now we need some mark steps. So this involves a little bit of tensor operations, because I think I'm going to be like initializing some tensors, and this involves also initializing some tensors. I think that stuff needs to be compiled. So after all of the initialization, I put in xla xm.mark step, and that will separate that code running on the TPU from what's happening in the first iteration of the training loop. I guess I don't need that if I just have a convention of putting mark steps at the start of each loop. I'm going to not put one at the end of the loop and at the end of the step and see what happens, because obviously we'll hit this one, and then if we are evaluating, we'll hit this one, and if we're not evaluating, we'll hit this one before we get to the next training step anyway. So I think adding these 3 mark steps should be sufficient to get up to this iteration speed. Oh yeah, the iteration speed is like the way that I tell if I've screwed something up, because
you only need one to get up to 60, which is just after the step, which is what the docs recommend. So you're doing something kind of fancier here, right? I don't know that the one that you're putting, like where you're doing the TQDM stuff, that's what the docs recommend. Yes, you're doing something cleverer. Yeah. What do you even?
Right.
Yeah. Okay.
Do you do this one?
No, I didn't do that one. I don't. Yeah.
All right, let's try it. I will put one after, just because we actually need to after the whole loop, because we want to make sure the final thing is evaluated. Actually, I guess that's not necessary. Because
it's not that it's
the final one.
It's not that it's not going to evaluate if you don't mark the step. It's an indicator.
Yeah,
to the
it'll
compiler.
evaluate by the time we need some strings. I just don't like thinking about lazy.
Yeah, well.
All right, let's try it with a much more minimal, and we can delete this one as well and see what happens. Okay. So I don't have as much diagnostics as going to moment. I don't know what that is. Not good. Oh, I'm already running something on this TPU, so it's crashed. So don't do that. But I will show you. First, we got a warning, and I'll talk to you about that. You'll see this if you don't include this or something to the effect of setting the environment variable PJRT device to TPU. But on the other hand, this is also interesting because this is how you would set it to CPU if you wanted to use XLA to compile to the CPU. In my experience, that doesn't lead to a speed up. Anyway, so there's this environment variable called PJRT device. And this does two things. First, it tells the XLA to target the TPU. And second, it tells it to use the PJRT backend, which is one of two different backends. I think the other one is called XRT, which is an older, this is sort of like the name of the actual compiler that does the compilation to the TPU. So you can, by just setting this one environment variable, you can remove both of these warnings, which tells XLA to use PJRT instead of XRT, and also tells it to target the TPU. And before you ask, I don't know what these stand for, so you'll have to look it up. That is XRT and PJRT. Any questions? Cool. Installed. Yeah, okay, I think that's all good. So I can't run this at the moment because this one is running, and I do want to let this one finish. It's gone pretty slow though. I'm not sure about that.
Just to confirm, Matt, on the last one that you tried to run there, where Dan suggested you just mark the step once, whereabouts did you do that?
Just after the optimizer step.
Mm-hmm. Reasoning being?
Well, this roughly separates the loops. What I think it's sufficient, other than what will happen is now, if there's any initialization operations that need to be compiled, you'll end up with a separate computational graph from the first iteration and the second iteration, because the first iteration is initialization and first step, and the second iteration is just training step without the initialization steps in the computational graph. So we'll have to compile that twice, but it's like mostly the same. So that's why I would think having one here would help, but that's worth testing actually empirically. The other thing is every time you do an evaluation, if you don't have another mark, you're going to end up with training step plus in this case, evaluation plus training step, versus usually it being just training step. So you'll have to compile that computational graph for sure separately. And so I think that's a good reason to put one at the end of the evaluation as well. Yeah, this speed is really tanked Oh, it's just come back up again. Well, there you go. But I don't know what's going on there. Yeah, I think I have some background reading to do to really understand how to do this in a more principled way. And also there's some profiling tools that you can use and some metrics, like how many compiles is XLA doing and how many of them are using the cache versus not, that would be worth investigating if you wanted to squeeze out some more performance. Okay, so it's 7. I mean, sorry, question?
Yeah. Can you say a bit more about what happens when you hit that mark step line? Like what does it do?
My understanding is that, let's say we're coming through a training loop, so it's just simple, or we've hit a mark step and then we skip the evaluation and then we go to the next step. What we do is we say, get a training batch, put it through the model, compute the loss, do an optimization step, like do a gradient descent step. What that actually does is just builds an abstract computational graph. It doesn't actually do any evaluations of the matrices in those matrix multiplications. It just builds a tree of matrix computations. And then it hands those to an optimizing compiler, which, for example, if there are temporary variables that we're assigning to involving copying like one tensor to another, but we don't actually need to be copying, it will like optimize that to be in place. Or if we're doing the matrix multiplications in one sequence and it can see like a faster way to achieve the same result, but by rearranging things like with associativity or something like that. I don't know this for sure, but I imagine it would do those kind of optimizations to the graph. And the main thing I think it does is like chunks up the computations into shapes that fit nicely on the TPU. So the TPU has like an 128 by 128 array of actual physical circuits that can do multiplications and additions for a matrix multiplication. So if your matrices and batches are like multiples of 128, then it works best. But even if not, it will like format them in a way, possibly adding some padding if it thinks it's going to speed things up. And it will find a way to optimize your particular computational graph for the specifics of the hardware. And then it will actually, after compiling that program to like a more efficient version of it, then it will actually evaluate those operations. And then you can proceed in the code to like do more and more training steps. Does that make sense?
Yeah. So the evaluation, you calling XM mark step is saying stop compile, like this is one subprogram, do the evaluation now and then continue. Right? Yeah.
The name of the method, that's right. The name of the method does suggest that it should be put here because it's for marking training steps. Okay, my CPU is finished. So that's nice. But I was previously using it as a way to like mark various different chunks of code that I thought should be compiled separately. And maybe that was slowing things down. Interestingly, now that the CPU is not running, this seems to be getting a little bit higher. So maybe that's why it was a little bit lower before. Forgot about that.
Or is the CPU
that matches my experience. Yes. Yeah, so even when you're using the TPU, it's still kind of doing things on the CPU. I'm not exactly sure what, but like if one reason why a TPU program can run kind of slow is if, for example, it's not using, so TPUs are really only good at like matrix multiplications and not that much else. So if your model involves doing things other than that, then it kind of has to move data back and forth between the TPU and the CPU, and that can slow things down. So to be clear, it needs to move it to the CPU in order to do the operation that the TPU can't do, and then it needs to move the data back to the TPU to proceed to the next matrix multiplication. That's another thing that the compiler figures out, like when to put those moves in, what to do on the CPU and what to do on the TPU. So it makes sense, and it matches my experience. I should have thought about this and reasoned why this was going a little slower than expected. And Dan, I would dare say that the 60 you were seeing was probably without a CPU being utilized, and maybe it actually doesn't make that much difference where the mark steps are, as long as you've sufficiently broken things up. Like if you just run without any mark steps, it's gonna not work because it will just try and run the entire training loop for 50,000 steps and then compile the whole thing, and that will not work. But if you just have it like at least one, possibly more, I would say that you probably get this kind of performance. Okay. So I think it's basically time to wrap things up. One thing I wanted to do, has everyone got a finished training run now, or some people still waiting?
I've got one.
Hopefully,
I got distracted
most
by
people have
doing parallelizing the loader, data loader, and shit like that. So I keep restarting it.
Okay. Okay, that sounds fun. You'll have to show me how to do that. What I was hoping to do is take a quick look at some of the things that the TPU, or in this case, the CPUs of the TPU VM, came up with for what should come next in the prompt. So what we've got here is my trained transformers thought it should be elementary my dealio for a rave of him, the smackle child, to know our cosing the ha for his you was a much under. And then I think this is at about 128 characters, which is the context window. It starts to go off into a little bit more nonsense. And so maybe that's like that's like a distributional shift on the context and something. But I don't know, it's doing some things. Like these are mostly word-ish or words, and it's getting the 4 spaces. It's getting the roughly the line length. So it's, it's not bad. Anyone else get something interesting, and please paste it in the chat. Through me is made, which into, that's much more coherent than my one for the start. Nice. Elementary, my dear, or before. A sum down, you have quite full C and end you, but the name, that's very, the most of those are words. That's amazing. Yeah, cool.
It reminds me of hitting the like suggested next word on your mobile keyboard.
Yeah. Nice. Okay, good job. Please do send me those when your training run finishes. I want to add them to this website. Here. I have a bonus question for you. Does anyone know how many times the famous phrase elementary, my dear Watson, actually occurs in the entire canon?
I do know, because I read your guide.
Okay. Anyone else? It is indeed 0 times. Never occurs. Wow, this TPU has gone off. Thinks there's a big break in the text. Yeah, it never occurs. So Holmes sometimes says, or many times says elementary when he's talking about his deductions, and he sometimes says my dear Watson when he's referring to Dr. Watson, but he never actually says these things together. And so there you go.
The same number of times as Vader says, Luke, I am your father.
Exactly. So sometimes humans hallucinate as well as language models. Okay, so we should have our research meeting, but let me quickly point you at what else is in here for your own reading that we didn't get to. So I have some notes here about how to get more of a speed advantage out of the TPU than we got. It wasn't super impressive. You can see that this took 21 minutes and this took 19 minutes. I think if we had have been running this while the TPU was off, we would have got more like 60 iterations per second in about 15 minutes, but it's still not like, it's on an order of magnitude over just running on a big CPU. Also, I'm getting comparable numbers on my, like not 10 times more on my MacBook. So it's not that impressive. But I think the main reason is because this model is pretty small and you get more of a boost to a larger model. Obviously, the training will also then take longer. It will take it will speed up by more on the TPU. That's my hypothesis. For example, the ICL experiments that we're doing, I'm seeing more of a speed up than this. And there's more about where to put the mark steps and how to profile. And I heard JAX does better, and you can also parallelize across. We're only using about a quarter of the TPU at the moment because it's got 8 cores. We're just using 2 of them. By default, you have to add some extra code to use the rest of the cores. If you want, it's now sort of know everything you need to know and more to apply for your own TPU allocation. This is a free 30-day allocation of 10-ish, I think, normally 10 TPU VMs that you can set up for free for the 30 days, and then you can ask to extend. So my experience with that is a bunch of people have told me that they're very generous with offering extensions to the allocation, and my 30 days is coming up in a few days, and recently I asked for an extension and they gave me an extension till December. So that matches my experience so far. This is also comes with Google Cloud Platform. So for some things to do on Google Cloud Platform other than TPUs, you will need to like pay for those other than the TPUs, which are like free during the allocation. But so far I've been spending my 90 days of starter credits that comes with just a Google Cloud Platform account. I can't remember if you have to be a student to get access to the starter credits or not. But so far, all that it's been costing me has been, I think, data. So if you're using it, network traffic. So if you're using, if you're sending like your model checkpoints, which we are for some of our experiments, to AWS, where we're storing them in a separate paid storage bucket, then sending that data through the network is gonna cost on the order of like $50 a month, or that's like roughly how much I've used for like the various experiments that I've done, which is not that many experiments, but it is, on the order of gigabytes or 100 gigabytes of data. I can't remember how much. And then I think you would have to be, once you pass the 90 days free credits, I think you'd have to be paying for this. I also don't mind if you use my TPUs, for example, for the hackathon, or if you want to keep playing around with them. I've got some guides here that I hope you would follow, but it's just basic stuff. So I'm not concerned that there's going to be any problems. And if you're interested in ways that you can try to improve the performance or like play around with this code, I think it's a good starting point because it's sort of a simple code base, so you can understand it and then run some experiments. So that's all from me. Sorry for going a little over time and not quite getting to the end in full detail, but yeah, hopefully that was useful and interesting.
I have a quick question.
Yes.
Okay. I'm wondering why we're doing all these compilation steps like in interpreted language. Like, would it make sense to, I don't know, do all of this ahead of time? I guess this is a 2-part question. Why Python in machine learning? And 2, the more direct question is, could like the computational graph we generate, it has like the different numbers in it each time, I'm assuming, but it's like the same shape, right? So why are we doing all this compilation effort every time?
Yeah, I agree with the spirit of this question. I think so. The Python is mainly used in machine learning because it's got like the ecosystem existing, so it's like a bit of a lock-in thing. But XLA is not specific to Python and also would work as a backend with, for example, Julia, which is a compiled data science language that might implement some of these kind of approaches that you're gesturing at. As for the compilational graph, specifically the data that is sort of logged is not the numbers of the matrices, but the shapes of the matrices, just the dimension, all of the operations. And then that is the sort of abstract computational graph that is compiled, because it shouldn't matter what the numbers are in terms of how to optimize it. And then so then in each training loop, we're running through that same computational graph using different actual numbers. For example, the weight matrices in the transformer are changing because we're optimizing them. We're doing gradient steps on them. So the same computational graph is used with different numbers, and that's what allows us to actually get this to work, because we can use the cached compiled computational graph.
Oh, okay. I thought it was taking effort each time to like recompile something, but
it is rebuilding the computational graph, as I understand, which is effort.
No,
but it's on the order of like.
I mean, if the shape of the tensors hasn't changed, the mark step, it's caching the compiled graph and then just executes it in place again. It doesn't. I mean, that's why you get
but in order to know that it's the same computational graph, it needs to build it. Like every time you run through the training step. But this is O1 in compared to like a matrix multiplication being order n to the 2.7 or whatever. Because just like specifying the shape of a matrix multiplication doesn't actually involve an order n operation. It's just an order 1 operation. So, but yeah, I think you could do more compilation and optimizations that would lead to more speed. And I think Julia would be the place to look for that.
Also, to answer that original question of why Python, it turns out that it's actually not that much slower when the slow thing that you're doing is usually like matrix multiplications, and those are all done either on CPU that's like they're efficient linear algebra libraries that are all written in C. That's basically all underlying like Torch and NumPy. Like basically like lab. Versus and if you're on GPU, you use CUDA, and TPU you use like XLA.
That's a good point. I think
it's all accelerated. Yeah.
So Python is kind of being used as just like a conductor that is like orchestrating the specific operations to do, but the individual sort of compute heavy operations are accelerated.
That makes the situation sound a bit rosier than it actually is. I mean, there are compiled kernels for certain operations, like the things that happen in transformers and other popular architectures. And so under the hood, what you're writing in PyTorch or TensorFlow or whatever gets compiled down very differently depending on the pattern of the thing you're doing. And if it's a standard thing, it might be very heavily accelerated. And if it's a non-standard, like new fancy architecture you're trying to create, probably it's much slower. And part of the heroic industrial level effort that goes into things like making transformers run very well is that people have sat down and written very fast kernels for GPUs that specifically work for these architectures. And that's like, so there's some insane like deep stack underneath Python which you don't see, mostly written in C++ or specific GPU driver languages. The orchestration is a good metaphor.
So Billy, you were also saying something there, but I missed it.
I just made a quip about tech debt. As it, like in other domains, I've heard some people have this perspective of only optimize the parts of your program that are like the hot parts of your code that need the acceleration, and then they find that like all of their little bits of unoptimized stuff kind of like adds up to their whole framework. But I don't know, like machine learning maybe is a different story, because if you're only doing this once and then you like the AI you use is completely independent of it, that maybe that tech debt isn't a problem.
All right, any further questions to Matt? No, let's thank Matt again. Thanks, Matt.
Thanks all for participating in your questions, and hopefully it was helpful.